Hi, everybody. We're going to wrap up chapter 12 with section 12.6, which is called cylinders and quadric surfaces. And I'll mention cylinders just a little bit, but quadric surfaces is usually the more important idea for this chapter as we go into Cal 4 when you start doing a lot more 3D shapes. So that's all we're doing in this section. So a quadric surface, that is a graph of a second degree equation in three variables. And so we could do an ax squared plus by squared and cz squared and all these other different terms if we wanted to. But through manipulation, you're going to get it down to one of two different forms. We'll either get it where you have uh, all three terms, the x, the y, and the z get squared, plus some sort of constant. And you can get this by manipulation with completing a square, for instance. Or you get this other version where you only get two squared terms and then one other variable to the first power. And you're going to be one of those two different things. And so I'm going to show you a chart in this section that will kind of help you pick off what different quadric surfaces you'll end up with. And so it's important to kind of visualize this. It's all visual 3D stuff. So if you're really good at visualizing three-dimensional space, this wouldn't be too hard. The hardest thing is just trying to keep which formula goes with which thing. So, for instance, what does y equal x squared look like in R2 in the xy plane versus the xyz plane in R3? Well, hopefully you know y equals x squared is just a parabola. That's a very simple parabola. And so if we were to extend that to the R3 plane or the XYZ plane, the three-dimensional space, what would that look like? Well, you have to keep in mind your z-axis is coming directly towards you. So you would get infinitely many parabolas basically stacked on top of each other. And so if I was to take this graph right here in r squared and rotate it a little bit so you could see the z-axis coming right at you, because the way if you look at it straight like this down from the z-axis, you would see this graph. But maybe we rotate it a little bit, to the right. You'd end up with a graph that looked like this. And so in my graph here, my z-axis is the one down here at the bottom. This is still the y-axis. This is still the x-axis. So all I'm doing is I'm rotating it slightly to the right so you can see that there are just parabola after parabola after parabola all stacked onto each other. There's a little line here, and a little line there, and a little line there, and a little line there, and there's all these different parabolas stacked on top of each other. And so anything from 2 space that would go to 3 space will just end up stacking that shape over and over again. That's actually how we'll end up getting the cylinders. So for instance, if I had x squared plus z squared equals 1, what is it and what would it look like? Well, what it is a circle if you're talking in 2 space. So if you're in just a xy plane, but technically here you're going to be in the xz plane because there is no y here, this would be a circle. Because if you have an xy plane, if it was x squared plus y squared equaled 1, if you had x squared plus y squared equaled 1, you actually have circles going around. This is your x-axis, this is your y-axis. You actually have circles going around your z-axis, because your z-axis would be the one coming out of the screen. Since we have x squared plus z squared, we're going to end up with circles with radius 1, but it's going to be going around the y-axis. So, sorry, yeah, the y-axis. I said that correctly. And so we'll end up with circles going x and z. We're in the xz plane. We'll have circles centered at the origin with radius 1 going around the y-axis. Now, if I were to tilt that to the side a little bit, one way or the other, since your z-axis usually goes up, maybe we could flip it and do the x, y, z thing like this. But your xz plane, which would go kind of like you're going to hit this point, this point, this point, and down here somewhere. So we're going to end up with circles. And I'll show you why I don't draw these usually out. But you're going to end up with circles that will be going around the y-axis. And so, like this. And you'll end up with a cylinder. I took that and stood it upwards, and made it look a little, not being a circle so much. But anyway, here's what it would look like if you were a good artist, not a me artist. I did not get into math to do drawings, so. But anyway, you end up with your circles. So if you kind of look right here, there's a circle going around the y-axis, and it is just infinitely many circles stacked on top of each other, and that's how we get our cylinder. Okay, let's try another one. This is kind of the same sort of idea. You'll notice you only get two variables, an x squared and a y squared. If you were talking about in a r squared situation, in a 2D space, this is actually an ellipse. An ellipse and a circle almost have the exact same equation. You have an x squared and a y squared that are added together equal to a number. But if you have different coefficients in front, like here we have a 4 in front of the x squared and a 1 in front of the y squared, since they are different coefficients, you elongate one side of the circle. That's where you get your ellipse from. This is x squareds and y squareds, so we're going to end up with ellipses that are just based on the xy plane. The y, the y has a coefficient of 1, and the x has a coefficient of 4. So if you wanted to, you could plug in what would happen if x were 0. If x were 0, then you'd get y squared equals 4, so y would be plus or minus 2. So you go 1, 2, 1, 2. So it's got to hit here and here. But if the y was 0, you would get x squared equals 1. So you're hitting here and here. So your ellipse is elongated along the y-axis. Again, that's all we would have in r squared. So if we tilt that and make it go around the z-axis, again, I'm going to try to give you kind of a representation of my own drawing first. The x, the y, and the z. Notice the z is missing, so we're going to be going around the z-axis. The x went to +1 and -1. The y went to +2 and -2. And so we have a ellipse laying in the xy plane, and then it's going to be just extending up and down, going around this axis. So hopefully you can kind of see that. If not, maybe a computer animated version would look a little bit better. But it's elongated on the y-axis, and it's just ellipses stacked on top of each other. And that's how we get another cylinder. And so this is one way that you can draw cylinders in 3 space. Now, like I said, most of the stuff that we're going to be doing is going to be quadric surfaces that are specific type shapes. So let's talk about what that would look like. So in your specific shapes, there's going to be basically 6 of them to work with. We have an ellipsoid, we have an elliptic paraboloid, we have a hyperbolic paraboloid, we have a cone, a hyperboloid of one sheet, and a hyperboloid of two sheets. And so our equations, kind of have those out there beside it, tell you what happens to draw these. What we'll do is we'll let one of those variables go away. You let x either be 0 or y be 0 or z be 0. And you figure out what kind of a shape you would have in the 2 space. And that would be a trace. So like on this ellipsoid, all your traces are ellipses. Because if you were to cancel one of these values off, you would end up with an x, either an x squared and a y squared, or an x squared and a z squared, or a y squared and a z squared equal to a number. That would be an ellipse. Now, if your numbers in front of the coefficients are the same, you actually get a sphere if all the traces are circles. A sphere is just a special type of an ellipsoid. Or if you have an elliptic paraboloid, some of your traces are ellipses, some of them are parabolas. A hyperbolic paraboloid, some of them are hyperbolas, sorry, I can't read, and some of them are parabolas. On a cone, everything is an ellipse for your traces, but your vertical traces end up being parabolas. Oh, sorry, hyperbolas, I can't read. And then your horizontal traces on your hyperboloid of one sheet are ellipses for the top parts, which is actually the same thing as it is for the hyperboloid of two sheets. You end up with an ellipse on the top. And then your verticals are hyperbolas, which are also hyperbolas down here. But what will happen is on the hyperboloid of two sheets, the two minus signs make it so that your graphs can't actually connect together. And so I'm going to show you a few different examples along for each one of these. So use traces to sketch out and identify the surface. So what we'll have here, I'm going ahead and tell you that this is an elliptic paraboloid. You can tell that by the equation, the x equals y squared plus 4z squared has the same format as the format for the elliptic paraboloid. You have a single variable on one side. It doesn't have to be z. The z by itself just tells you that the elliptic paraboloid will go around the z-axis. So in ours, we expect our elliptic paraboloid to go around the x-axis. And then we'll have a squared term plus another squared term. Well, that's what we have, y squared plus a 4z squared. And so what we'll do is we'll try to do traces to see what happens along the way. Like, for instance, if you were to eliminate one of those, either the x, y, or the z, if I was to eliminate, let's eliminate the z first. If z equals 0, then I would have x equals y squared. These are parabolas. Just like y equals x squared opens up around the y-axis, x equals y squared opens up around the x-axis. So we have parabolas on the x-axis. If you let the z or the y be 0, I already did z, y be 0, you get x equals 4z squared. These are also parabolas. Except instead of now using a y squared, they're opening up around the x-axis as well. They're opening on the x-axis, but now they're in the xz plane instead of the yz plane. And if you let the x equals 0, and by the way, it's not technically 0. You're really letting these things be constants. That might be, the 0 is going to make it kind of confusing on this last one. So it's technically, you're letting it be just a number. It could really be any number. But if it could be any number, it could be 0 as well. So that I think it helps to see the zeros if you can use the 0, but it won't make any sense on this last one, because on the last one, if it was 0, you just get y squared plus 4z squared equals 0. That's just a circle with no radius. So if we let it be a number, this is where you get your ellipse. Ellipse. I don't know. Spell ellipse any way you want to. So what I tried to do here is, instead of my really ugly drawings, I thought I'd show you what would happen on each one of these. So here is my situation where I'm in the xy plane. So this is where my z is equal to a number. So I get parabolas going around the x-axis that are based in the xy plane. So this first one goes for when z is a number. If I was to let y equal a number, I would get parabolas going around the x-axis based in the xz plane. So your parabolas are turned sideways here. If you notice, they're going sideways. So you get parabolas in the xz plane. Or if you were looking at letting x equal a number, you would get ellipses. And that's what this is. We have ellipses going around the x-axis. These are based out of the yz plane. Oh, sorry, yz. Yeah, that's what I said. Yz plane. So you'd have an ellipse going around the axis here. And then you're extending that out. You put them all together. If you laid all three of those different traces on top of each other, you would get a graph that looks like this. It is a elliptic paraboloid opening up around the x-axis. Hopefully that makes some sort of sense. I won't go through that much detail on every one, but I will show you what the traces come out to be along the way. This one is a ellipsoid. Ellipsoids are ones that are coming out as ellipses on every single trace. It's an ellipse if you have all the squared terms, the x squared, the y squared, and the z squared in the problem. They're all positive and they're equal to a number. So this would be this left-hand side here. You have x squared, y squared, and z squared all added together. And then you have a number on the other side. In this case, we have 36. You could get it to the 1 if you wanted to. And I'll show you how to get it into that standard form if you want to do that a little bit later. But it is a ellipsoid, and so I'm going to do sort of the same thing. What if z was just a number? And so, since it won't make a whole lot of difference, I'm just going to pretend like it goes to 0 here. And so I would get 4x squared plus 9y squared equals 36. This is an ellipse. Since we're taking the z out, this is an ellipse going around the z-axis. If you had y equal a number, then you would have something like 4x squared plus 9z squared, which is basically the same thing we have when we let z equal a number. That's also an ellipse. With the y missing now, we're actually going around the y-axis. And with x being a number, then you get 9y squared plus 9z squared equals 36. This is actually a circle going around the x-axis. A circle because the numbers in front of the z squared and the y squared are actually the same number. So if they match, you actually get a circle. And what does that look like? Well, kind of like this. So we get ellipses going around each one of the axes, except the one going around the x-axis. That would be, if you can kind of see it, there are some green ones on the graph right here going around. That one actually comes out to be a circle. The other ones, there's an ellipse going around the y-axis, and there is a ellipse going around the z-axis up here at the top. So that's our three different shapes. Okay, this one is a cone. I know it is a cone because we have a single squared term on one side. It doesn't matter that the formula on the right hand side has a z squared on it instead of an x squared, but you have a single formula, a single variable that's squared on one side. The other terms have to be squared on the other side, added together. In the generic formula on the right, notice the z squared is by itself, so the z is the axis it goes around. In our case, the x squared is by itself, so it should go around the x-axis when we do this. We'll get hyperbolas, and we'll get ellipses. So, if I were to let z be a number, pretend like it just goes away. Then I get x squared equals 4y squared. That's a sorry. This is going to be a hyperbola. Because you get a squared on each side, you could subtract the x squared to the other side and just get a number on that side. That would be your z. Since they're subtracted, this is going to be a hyperbola. If you let y be a number, you'll end up with the same situation. You'll get x squared equals z squared, or x squared minus z squared equals a number. That's also a hyperbola. But if you let x be a number, you'll get a number equal to 4y squared plus z squared. That is your ellipse that we just looked at on the last problem. Your numbers in front of your squares are different. It's equal to a number. That would be your radius squared, basically, kind of like if you're doing a circle. And so you'll get hyperbolas and ellipses. That ellipse, since the x equals the number, is going to go around the x-axis. So what does that look like? Well, it looks kind of like this right here. So if you look kind of closely, there's a green ellipse going around the x-axis. But there are hyperbolas going around the other axes. There's the parabola. One parabola would look like this, or a hyperbola. I keep saying parabola, but I mean hyperbola. There's a hyperbola going like that. There's also going to be a hyperbola going around like this. So there's hyperbolas on each one of the other axes. Around the x-axis, you're having your ellipses. Okay, how about this? We have, in this case, I don't know why these have extra variables on them. I'll just erase those. We have z squared minus 4x squared minus y squared equals 4. This is going to be a hyperboloid of two sheets. Really the only difference between the hyperboloid of one sheet and the hyperboloid of two sheets is an extra negative sign that you pick up. But this looks like this equation over here. Notice the z squared is positive. Our z squared is also positive. So our shape will look almost identical to this one that's in this little baby graph right here. The z squared that's positive tells you which one is going to rotate around, which axis is going to rotate around. And so if I were to let z be just any number, like for instance it could be 0, but It was just a number. Just pretend like it goes away here. We'll end up with negative 4x squared minus y squared equals 4. That's going to be your ellipses going around your axis. It looks kind of goofy here. We have two negatives, so you could divide everything by a negative if you wanted to make them positive. To see it's an ellipse a little bit better, but it is an ellipse. The reason why, if you divide by the negative and put the negative on the other side, that's how we're going to end up with a gap in between our two graphs, because you can't have those negatives involved. If your y was a number, we'll end up with like z squared minus 4x squared equals 4. Here you have two squared terms that are subtracted, so that's where you get your hyperbolas. And same thing, if I let x equal a number, I'll get z squared minus y squared equals 4. Again, you get two squared terms that are subtracted, and so we'll end up with another hyperbola. And so if you do ellipses and sets of hyperbolas going around as well, you'll end up with, like I said, basically the same shape we have up there. The only difference is how it's elongated. So we're going around the z-axis. That would be your ellipses. So you notice across the top here, there are ellipses going around. So there's your ellipse. And then we have hyperbolas everywhere else. So there's a hyperbola kind of on the inside going this way. That would match with the hyperbola that's down here. Or one on the outside maybe would be better to draw. There's one there that matches with the one that's like right here. And then there's hyperbolas on the ends as well. There's some that are going around this axis that would match with this axis. And so it's kind of hard to visualize sometimes, but if you can get those traces down, and on the homework you'll have, you won't actually be drawing any of them. They're all multiple choice to pick off the correct graph. Okay, this one says use traces to sketch the curve. This one's a hyperboloid of one sheet. This one's not quite in the correct form though. Notice our form over here has all the squares on one side with the number. This one does not. So if I rearrange it, this would be 9y squared plus 4z squared minus x squared equals 36. Then we have it in the correct form. The 9y squared, 4z squared, and x squared. Notice the z squared is the negative term in our generic version over here. The generic version has the z on it. And so we're going around the z-axis. So here the negative is on the x squared. We will go around the x-axis. So that is kind of nice to notice. If I do my traces, what I actually end up with, if z is just a number, then I'll end up with 9y squared minus z squared equals a number. This is your hyperbolas. Hyperbola. Because you have two squared terms that are subtracted. If y is a number, you'll get the same sort of thing. You'll get 4z squared minus x squared equals a number. That's also a hyperbola. Again, for the same reason, you have two squared terms that are subtracted. And if your x was a number, you'll get 9y squared plus 4z squared equals a number, 36. And if you want to leave it like that, this is an ellipse. Now the difference, there's an opposite in the wrong spot, but whatever. The difference here over the last one is the fact that we have positives all the way through. And so the positives all the way through on my ellipse, other than the last one, will allow me to be able to connect the graphs together. And so our graph would look something like this. Going around the x-axis, when your x is a number, you end up with ellipses. So if you'll notice, there's an ellipse right here. But then I have hyperbolas everywhere else. And so these hyperbolas, you would have one going across this way that matches with the ones that's going down this way. And then we also have hyperbolas going this way and this way. And right when they hit in the middle, you'll notice there are two straight lines. If you can kind of see those two straight lines tell you that that's where it's going to hit at the origin. And so we have ellipses and parabolas that connect together. So hopefully this is making some sense. Okay, let's do another ellipse. This one's a little bit more like the generic version here because of the fractions involved. But it's the same sort of idea. You have an x squared, a y squared, and a z squared all added together on one side. Notice the 9, 25, and the 4. One thing that you can really notice here is since it's a 9, 25, and 4, those are perfect squares. And so it's really easy to graph these because the square root of each one of those numbers is how wide it would be. So if you're 9 on the bottom, you're going to go between -3 and 3. 25 tells you you're going to go between -5 and 5, and the 4 on the bottom says you're going to go between -4 and 4. If you wanted to draw a really nice graph, you could do that sort of thing. I'm going to do the same thing I was doing. If z was just a number, we'll end up with x squared over 9 plus y squared over 25 equals 1. This is an ellipse. You have two squared terms that are added with different coefficients in front of them. If your y is a number, you'll get the same sort of thing. Two squared terms that are added, that is also an ellipse. Or if your x is a number, you'll get two squared terms that are added. That is also an ellipse. So you're looking at ellipses going around each one of the axes, which would look sort of like this. Notice it's kind of elongated on the y-axis. That's because of the 25. You have to go between -5 and 5 on the y-axis, whereas it's kind of short and kind of flattened on the z-axis. That's because that's the smallest number. The 4 on the z squared says you're only going between -2 and 2. But we have ellipses on each side. There's one right here going around the y-axis. There's one right here going around the x-axis. And there's one on the top going around the z-axis. And so that's your three different ellipses. Okay, this one is a hyperbolic paraboloid. Now, there is no way in the world that I will draw this in any way, shape, or form. So even if I attempted to draw those other ones by hand, they might sort of resemble something. This will not resemble anything. But it is a hyperbolic paraboloid or a saddle. Sometimes they're called saddles because, for obvious reasons, they kind of look like a horse saddle. It's a saddle or a hyperbolic paraboloid because we have this sort of form. We have a single term on one side and squared terms subtracted on the other side. So my single term is the y, and my subtracted terms are the z squared and the x squared. And so if I was to let z equal just a number, I would get y equals -x squared. Well, that's nice. That's just a parabola. And I actually mean parabola this time, not hyperbola. That's a parabola. In fact, that's a 2D space one that's very familiar to most people. If your y is a number, then you'll get a number equals z squared minus x squared. You have two squared terms that are subtracted. That's where your hyperbola comes into play. And if your x was a number, you get y equals z squared. That is, again, a parabola. The y equals x squared has your graph opening around the y-axis. Y equals z squared will have it opening around the y-axis as well, just in a different plane. So what does this look like? Well, it looks kind of like this, which is why I really did not want to draw this one. You have parabolas. You have, like I said a while ago, the z being a number and the x being a number. You get parabolas. They're both y equals something, so they're both parabolas opening up around the y-axis. One of them is kind of easy to see. You have one that's going right here. There's a parabola right there. The other one is not easy to see because it might be actually easier to look at the generic version up here at the top for a moment. You'll have a parabola that's opening this direction, but you'll have a parabola opening underneath it, kind of like this. And so here, there's a parabola on the back side of this thing going the other direction. That's kind of hard to draw here. And then your hyperbolas are on, well, actually, I might could kind of highlight those parabolas. There's one, you can kind of see it. It's kind of going this way and then rotating around. So it'd be going down the backside. But anyway, and then you have hyperbolas as well going around the y's as well. Okay, so this one says reduce the equation to one of the ones in standard form. And so I'm going to kind of cheat on these just to show you that what we're kind of aiming for. This is going to end up being a hyperbolic paraboloid. When it says to write it in a standard form, they want you to get it into that into this box over here on the right hand side. This little z over c equals da 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 da. In our case, though, since we have the y to the first power, we're going to get it into the y by itself. So if you ever have a single term by itself, a lot of these formulas have that letter by itself already. So the 2y, I'm going to get it by itself and move the 2z squared and the x squared to the other side. Now notice that the z, the x squared, and the y squared in the generic version all have coefficients of 1. So I want to get a coefficient of 1 everywhere. And this one's pretty easy to do that. I just divide by 2 everywhere. And so I get y equals z squared minus x squared over 2. And officially, if you want to get it into super generic form, you would actually need it to have a number squared on the bottom. So it's really root 2 squared. If you didn't go that far, it wouldn't make a whole lot of difference. But because you can get it into a term of a single variable on the left-hand side and 2 squared terms subtracted on the other side, that's why this is a hyperbolic paraboloid. Okay, same idea here. We're going to try to get the terms all to kind of match up this formula on the right-hand side. What we have here is all 3 squared terms on the same side. And usually if you have all 3 squared terms that are squared in there, they usually try to keep them on the same side. And so that's what we'll do here. If I subtract the x squared and the z squared to the other side, set it equal to 4, then I have 2 squared terms that are negative, 1 squared term that is positive, and then I got to have coefficients of 1 all the way across. So we're not going to divide by negative 4, but we're going to divide by just 4 everywhere. Because we can't have that 4 in front of the z squared. We also would like to have it equal to 1. And that's kind of another goal that we're aiming for here. So this is technically negative x squared over 2 squared. This is z squared. This is y squared over 2 squared. And this is 1. And that's your super generic form for your hyperboloid of 2 sheets. Okay, this one you have to do a little bit more work on it than that. Reduce the equation to one of the standard forms. This is actually going to end up being a elliptic paraboloid. So we're going to get ellipses and parabolas if we were to graph this thing out. But here, to get it into that sort of form, we're going to have to do a few different rearrangings. For instance, notice I have an x squared and a y squared, and I have a single z term. In my problem, I have an x squared, a y squared, and a single z term. But I also have a 2x and a 6y. That lets me know that I'm going to have to complete the square. So I'm going to get them together. I'm going to do the x squared minus 2x and put the blank. This is very much like we did in one of the other sections earlier. The y squared, the minus 6y, and a blank. And then I have the minus z. I'm going to go ahead and move the 10 to the other side. And so I take half the number and square it. And so I'll add 1 to that side. And I'll take half of the number. So half of 6 is 3. 3 squared is 9. So I'll add that to the other side as well. The first 3 terms factor into x minus 1 squared. The next 3 terms factor into y minus 3 squared. Then I have a minus z equals 0. Now, since it all canceled to be 0, that's good, because if you notice, our generic version doesn't have a constant sitting out there. So we would just move the z to the other side and say that z equals x minus 1 squared plus y minus 3 squared. So we have a z equal to a squared term plus a squared term. That makes it be your elliptic paraboloid. Now, we didn't graph one with a x minus 1 or a y minus 3 in it, but what that does is it shifts it off of the origin. Every graph that we looked at so far is at the origin, so the x squared and the y squared could be shifted left or right, and those numbers inside the parentheses, those make that shift left or right on the x-axis or the y-axis. Okay, I'm going to do the same sort of thing on this one to reduce this one to a standard form. Here, this one's going to end up being a cone. So we're aiming for basically squared terms everywhere except 1 on one side and the other 2 are on the other side. So we should have squared terms all the way through on this thing. I have an x squared, a y squared, a z squared, 4x, a 2z, and a 3. So the z squared that's in my generic one that's going around the z-axis is going to end up being my y squared in this one because there's no other y's in the problem. So I'm going to leave the y squared by itself. And I'm going to move, no, sorry, I said that wrong. The x squared will be the z squared because the y squared and the z squared are both negative. I would have to move those to the other side. So I do need to complete the square though. When I complete the square, I need nothing in front of the square term, so I'm going to move the negative ones to the other side. So I'm going to do it x squared, 4x, and the blank. And I'm going to go ahead and move the y squared to the other side and the z squared with the 2z. So I'll have a blank on that one. And I'll go ahead, it doesn't matter which side you leave the 3 on, because since there is no constant in the generic version, that 3 should cancel off. And it will. So if I take half of 4 and square it, half of 4 is 2, 2 squared is 4. So if I add the 4 over there. And if I take this 2, and say half of 2 is 1, squared is 1. So I added 1 to that side so I could subtract 1 from that side as well. Again, notice the numbers cancel all off. So this is x minus 2 squared. This is y squared. And this is z plus 1 squared. And all the numbers cancel. So I end up with a squared term equal to a squared term plus another squared term. That gives you your cone. Again, the -2 and the +1 inside the x's and the y, the x's and the z's, those will shift your graph 2 to the positive direction on the x-axis, 1 to the negative direction on the z-axis. Okay, how about one last problem? Sketch the region bounded by the surface for z equals the square root of x squared plus y squared, and it's bounded by the x squared plus y squared equals 1, and between from 1 to 2. So we didn't really have anything that had a square root in it. So if you took the square on both sides, you might remember this is your cone equation. If your z was just a number, then we get a number equals x squared plus y squared. That, in this case, actually are circles, because your coefficients from the x squared and the y squared is the same one. If you had y equal to number, you would have z squared equals x squared plus a number, or z squared minus x squared equals a number. This is where you pick up your hyperbolas for your cone. And same thing if you let x equal a number, you would end up with z squared equals a number plus y squared, or z squared minus y squared equals a number. Pause for a moment, the pen stopped writing. There it goes. Y squared equals a number. So this is another hyperbola. So this thing has to be a cone. Technically, because it's the square root on the right-hand side, you're actually only going to end up with the top half of a cone. The other part, so this piece right here, is actually the top half of a cone. The other part, this is like one of our cylinders we were talking about earlier. X squared plus y squared equals 1. That's just a circle going around the z-axis. It circles if you just look at x squared plus y squared. So if we tilt that and see that it's actually going around the z-axis, we'll make a cylinder. So this is going to be a cylinder. We bound that between z being 1 and 2, and you'll end up with a graph that kind of looks like this. So this is your outside part is your cone. Your inside part is your cylinder. So the region is in between the cylinder and the, like on the top part up here, we have a circle on the top part. That's your, when your z is a number, you're getting circles. And so we have these circles that are the outside of the boundary. The cylinder is the inside, and we're getting basically the donut part. And so that tapers off going down because it's inside of a cone. And that is quadric surfaces. So hopefully some of that made some sense. And then we're going to start chapter 13 with only 4 sections to go.